Okay, so here's yet another video for class 13, another example. I did too many, but here's a very common one to have for linear momentum. It's for a jet to try to knock over this block. So we have a 10 millimeter diameter jet of water is deflected by a homogeneous, one of those words, rectangular block, which is 15 millimeters by 200 millimeters by 100 millimeters, right? I think the 200 millimeters must be side to side. And it weighs 6 newtons, that block does. Determine the minimum volume flow rate needed to tip the block over. So this is this problem right here. And I guess starting out here, one thing, let's write out an assumption. Assume that this beta, this flux, this correction factor is going to be 1. So here is an FBD of the block by itself. And what we expect to find is some kind of force that is being applied right here. We call it F. That's going to knock it over. And so when it starts to get knocked over, it's going to tilt ever so slightly. So it's really going to be, before it starts to really knock over, this part of it's going to, we assume it's not going to slide, because they say it's going to tip over, right? So that means that this is not going to, the block's not going to slide. So it's going to have maybe get stuck right there. So that's going to be where we're going to have some reaction forces that are going to be taking place right there at that corner. We also know the other force. This thing, we know how much it weighs, so we have the weight acting right there. So what we should do, let's call this O right there. I kind of want to call this. Let me rename these. The hair falling out. Maybe get a haircut. Maybe that's the reason why your hair's too long. It's gonna start falling out. And we got a Rox and we got a Roy. I decided to call that O instead. So I'm going to take the sum of the moments about O equal to 0. And we will take this F. And it's going clockwise, so it's negative. And it's going to be half this distance, which is going to be 0.05, right? It's 1/2 of the way up there. So that's the distance right here perpendicular to it. And then it's going to have a counterclockwise around here of the weight. So it's going to be plus, and that's going to be 6 newtons. That's going to be 1/2 of this width, which is 0.015 divided by 2, and that's going to be equal to 0. So the force to tip this thing over is going to find out to be 0.9000 newtons. Right there, because we did it about here. We didn't need to find these, but we would then be able to find what they're equal to, but that doesn't matter. What we really care about is what this F was going to be. So that F is going to be the force because of this flow that's happening right here. So let's do that's right here is just some statics. Let's do the fluids portion of it. All right, so we're going to have to be a little bit clever here. We don't know what this and what that is going to be. So let's draw our control volume. It's going to look like that right here. And we're going to have it right into there, right? Let me draw an FBD of the control volume and a momentum diagram of this. So it's going to be a square. And here is going to be the control surface. And here's an outlet control surface. And for this one, let's pretend the thing is just going to dribble, right? It's going to dribble down here. So here's a control surface too. So we can go ahead and sketch these things in here, but all we really care about is what's happening to these control surfaces right here. But not yet, right? So we're going to pick just outside over here. So we're going to have atmospheric pressure here, atmospheric pressure here, atmospheric pressure here. But here on the FBD portion of this thing, we're going to have the reaction in the x direction because of this thrust. That's going to be the Rx. Note that the Rx is going to be equal to F. These are equal and opposite. We separated out this thing from this in order to expose that. Through this control surface, we're going to have the m dot V1 coming into that thing. And we're also going to have coming out of here, we're going to have an, let's call this m dot 1. And it's going to have m dot 2 and V2. And let's have right here coming out of that control surface m dot 3 and we'll say V3. Now, let's just say m dot 1 is going to be equal to m dot 2 plus m dot 3, right? Because with the conservation of mass means these two outlets need to equal this. Let's also assume that V3 is very small. Let's just say that the thing is, it's going to be spreading out and thin. Like, you know, if we were looking down upon this thing, it would also be coming outwards this way. So it's going to be so small that it's not going to really affect the x direction, because we're going to apply our sum of the forces on the control volume are going to be equal to the sum of the forces beta m dot v out minus sum of the betas m dot v, and that's all the in right there. So yeah, so in the x direction here is the only one that we're really going to care about. And they're going to be, notably, we already decided that's going to be negative. We've just decided that must be, right? Because we know it's opposite of this. And we know it's going to be equal to that. So we're going to assume that this is very, very small, the outlets. So all we have is the inlet, which is negative, which we predicted, right? Because we know that the inlets are negative here. But also, this velocity is the opposite sign of the outward normal. So that's what this negative already is telling us from the Reynolds transport theorem conclusion that we had in that equation. Let's say, what equation did we use? We said this was our main equation right here that we're going to. And this right here decided what the signs were going to be. So that's equation 618 in our textbook right there. And so that dot product is the one that made this right here a negative value. Okay, so just recalling why we're having this sign, these signs happen. The beta is going to be 1 m dot. Let's see. Let's make sure that m dot 1, m dot is going to be equal to rho. Let me go A1. A1 V1, right? So we're going to have rho of this is this. These are in meters. Yes, these are in metric, right? So that's going to be 1.9. No. 999. 999. Ooh, I know what I did here. Let me go back. I liked how I did this. Let me keep it as values. So I went beta rho A1, and then V1, and then V1, right? Because that right there was the m dot, and that one right there is the velocity onto the thing. Anything else? No. So if we want to solve for the velocity, we don't know the velocity, so we're going to taking in those cancel out right there. So we're going to have the F divided by let me keep the beta in there, because it could have mattered. Beta rho A1. And so we know this. We know that this is 0.900 newtons. We got that from up here to tilt the thing. Beta assumed as 1. 999. And this was a circular cross section of 0.01, right? So it's 10 millimeters, or so pi over 4, 0.01 squared. And we get a V1 equal to 3.387 meters per second. So the volumetric flow rate, which is, I believe, what they were asking, A1, V1, and so we could have found this area before, but we'll just keep putting it in there. Why not? 3.387. Is that right? Yep. I think I got that right. And we get 2.660 E minus 4 cubic meters per second, but it's really small. Let's turn it to liters. We know that there's 1,000 liters in a cubic meter, right? So we can multiply by 1,000 and end up with a 0.2660 liters per second is going to be the answer. Liters per minute might have been a better one. We get a larger number there, but we could picture how much this is to be able to, as they were asking, knock this block over. That's the end of this video.